Hello and welcome to the AI Research Roundup. I'm your host, Alex. Today we're looking at a really interesting paper titled, What Kind of Visual Tokens Do We Need? Training Free Visual Token Pruning for Multimodal Large Language Models from the Perspective of Graph. So, these large models dealing with images and text often use a huge number of visual tokens, right? Which leads to a lot of computation and redundancy. This paper asks, well, what tokens do we actually need? They found that surprisingly both foreground and background tokens are critical. They then propose a neat training-free method called gprune, using graphs to prune these tokens, keeping the important ones and significantly cutting down computation while keeping performance high. Okay, so figure 1 here really shows some of this in action. Part A on top plots the accuracy for different pruning methods. You've got random, foreground only, background only, and then gprune in red. See how gprune maintains much better accuracy, especially on text VQA, even when pruning heavily? Then, Part B shows the L2 norm distribution for an image. Notice the overlap between the foreground in blue and background in red, suggesting important tokens aren't just in the obvious foreground areas, which backs up why we need a smarter approach like gprune. Okay. So building on that idea of using graphs, Figure 2 actually visualizes the gprune method step by step. First you see, in part A, they extract the visual tokens from the image, like breaking it down into patches. Then, and this is the key part, in B, they build a graph. Connections are made between tokens that are semantically similar, based on cosine similarity. Following that in Circa, there's this iterative process called information propagation, where the importance score of each token gets updated based on its neighbors in the graph. Finally, the method selects the top K tokens with the highest scores, effectively pruning the less important ones while keeping representative tokens from all over, like the dog's face and the grass here. Okay, so Figure 3 gives us a broader look at how gprune stacks up against other compression methods like FastV and ToMe across several different benchmarks. We're looking at accuracy versus flops reduction again, similar to what we saw in Figure 1 Part A. What's clear across text VQA, DOC VQA POPE, and GQA is that gprune, the red line, consistently maintains higher accuracy compared to the others as the flops reduction increases, meaning as we save more computation. It performs particularly well on those detailed tasks like text VQA and DOC VQA. Alright, moving on from those graphs. Table 1 gives us the hard numbers comparing gprune with other methods like random ToMe and FastV across a whole bunch of benchmarks. This is all using the LLAVA Next 8B model. We see different pruning ratios, 50, 70, and 90%. Just look at the 90% pruning on text VQA. gprune scores 59.31, which is way better than ToMe's 38.36. And it also boosts throughput significantly, like nearly 2.8 times faster at 90% pruning. So yeah, it really holds up well, especially on those tough tasks, even when removing most tokens. Okay, so Figure 4 provides another angle on gprune's effectiveness this time, specifically comparing it against just using the L2 norm for pruning. The plot shows the average score across GQA, POPE, and text VQA against the pruning ratio. Again, gprune is the red line. L2 norm is light blue, and the baseline is the dashed black line. You can clearly see gprune stays much closer to the baseline performance, especially as you prune more heavily, while just using L2 norm drops off quite sharply. This really underscores the benefit of that graph-based information propagation step in gprune. So we saw gprune beats L2 norm pruning, but what makes gprune itself work so well? Well, Table 2 digs into that with an ablation study, basically breaking down gprune's parts. It shows performance on GQA POPE and text VQA, comparing different setups like using just L2 norm, just the graph, or both. You can see using both components, which is the full gprune method, gives the best average score of 72.04, That's super close to the baseline average of 72.88, but with significantly fewer TFLOPs. This really confirms that both the L2 norm initialization and especially that graph propagation step are contributing to its success. Okay, so we just saw that the graph propagation step is important. Table 3 here digs a bit deeper into gprune settings, specifically the number of propagation iterations, T, and the similarity threshold, S, used to build the graph. Looking at the average scores across those same benchmarks, GQA Pope and text VQA, it seems like the performance is pretty good when the iteration number is around 5, and the similarity threshold is between 0.5 and 0.7. It shows the method is quite robust, but these settings seem to hit a sweet spot for performance. So yeah, those settings seem to really dial gprune in. Overall, this paper introduces a really neat training-free method, gprune, for making these big, multimodal models more efficient by pruning visual tokens. The key insight is using graph propagation to keep the really important visual information. This kind of efficiency improvement is super important as these models get bigger and bigger. Well, that's all the time we have for today. Thanks for tuning in to the AI Research Roundup. I'm your host, Alex.